Okay, so let's go ahead and move on to the carbon cycle as it occurs in the water, specifically within the ocean. So I do have a page for you guys to draw this carbon cycle. I just wanted to give you a sort of a quick look so you can think about where to place things on your page as you write your notes. All right, so as we said earlier, there is this atmospheric pool of CO2 in the air, and some of that carbon dioxide is going to dissolve into the water and undergo its, a separate set of similar but somewhat different processes once you're in the water, specifically in the ocean. So on your aquatic carbon cycle page, go ahead and draw yourself a happy little ocean. Maybe you have yourself some happy little clouds, whatever you like. Um, so we have this atmospheric CO2, and as I said, some of that CO2 is going to dissolve into the water. So if you've, ever noticed the bubbles that are present in like your Coke cans, that is dissolved CO2 in your soda. So same deal, that gas will go into the water. And just like on land, it's going to be picked up by the resident producers and autotrophs. So in this case, in the ocean, that is primarily the phytoplankton. And just like those land plants, those land producers, they use photosynthesis to take that CO2 that's in the water and the sunlight, and they use that to make glucose, which then forms, the energy availability to the other organisms in the ocean. So same deal. But because this is the ocean, a lot of things are happening to that carbon dioxide chemically that don't occur on land. And so the CO2 that is dissolved into that ocean water is going to combine with these free hydrogen ions and make something called carbonic acid. So this is just something that's going to happen. And we'll come back to this one later because it's kind of causing us some issues. But it can also undergo further chemical reactions, becoming bicarbonate. So that's something that you might find in like your baking soda. And that bicarbonate can combine with calcium to make calcium carbonate. And the reason that we care about calcium carbonate is that the mollusks and coral will use that calcium carbonate to make those hard protective shells. So whether you're a coral or a clam or a snail, you're taking calcium carbonate that's available in the environment to make that protective shell for you. Now, just like on land, sad things happen. And snails and clams and corals will eventually die. But when they become buried in sediment and over millions of years, their bodies become limestone, which is probably familiar to us here in Texas. We are sitting on one of the larger limestone deposits in the country. So that means that, millions of years ago, Texas was laying on a bunch of, we used to be ocean. Basically, that's the only way it could have gotten there. Okay, so back to this carbonic acid, right? So as I said, CO2 is going to be converted into carbonic acid, and the rate of this transformation is based on how much CO2 is in the atmosphere. So if there's more CO2 in the atmosphere, that's going to be more CO2 that's dissolved in the ocean and result in a higher level of carbonic acid, which is going to make the entire ocean more acidic. So why is that a problem, right? So we're going back to your notes, right? So that carbonic acid will lower the pH of the aquatic environment. And so think back to like second grade when you were doing like your play volcanoes, right? So what do? We add baking soda, which is basically bicarbonate, to an acid, so something like vinegar. So what happens when you add bicarbonate and acid together? You're going to get, this huge fizzy thing, you get this huge explosion. Well, chemistry is the same whether you're in the ocean or in your kitchen, and basically the same thing is going to occur with our poor little animals, right? So the mollusks and the hard coral use that calcium carbonate to create their solid structures and skeletons. So it's a problem when the pH drops because it's going to dissolve those shells, and it's going to basically kill them, right? So that's our poor mollusks. So just to go over the limestone. So when they die, and over time, they're sort of similar to the process of the fossil fuels, that calcium carbonate will get converted into limestone. So if I were to ask you how is limestone formed, you would know that marine organisms absorb CO2 in the form of calcium carbonate to make their shells, and that when they die, their shells accumulate on the ocean floor, and that over time the rock layers will settle on them, and that heat and pressure over time turns into limestone over millions of years. So that's how we get limestone. But let's go back to this ocean acidification. So as you guys probably already know, there is a problem with increasing CO2 with increasing carbon dioxide levels, and it's causing a lot of issues as far as like the temperature on the earth, but it's also increasing acidity in the ocean. So if I look at my graph here, and so just take a moment and think about what this graph might be saying. So when you're looking at any graph, first thing you're going to look at is the title. So okay, we're looking at ocean acidification of CO2 and pH, and we're looking at a time series in the North Pacific. So if I look at the x-axis here, sure enough, I'm looking at years. It looks like it starts in 1960, and every one of these is a 10-year, and we're over here at 2010. And if I look at my y-axis, I'm looking at CO2. That ppm just means parts per million. So for every, molecule, every million molecule of air, this is how many parts per million is CO2. And where this is not starting at 0. So just be wary when you're looking at graphs like this when they do this, because I always think that's tricksy. So it's not starting at 0, but we go up to about 400. And what do you think this curve is showing? So when I look at this, it looks to me like over time, CO2 parts per million. So carbon dioxide levels have been going up kind of in a linear way over the last 50 years or so. So that's just carbon dioxide in the atmosphere specifically. So it seems like CO2 levels are rising. So when I add this other little thing here, so this is saying it's something different. So this is CO2 dissolved in surface seawater. So, and again, this looks like a smaller line here, and what's interesting to me is it's all over the place. So this one seemed much tighter, but okay, they ran their math on it, they came up with this line, and it does seem to me that the dissolved CO2 is on the whole going up since 1990, and I have suspicions about where this sort of yo-yo pattern is coming from. So it makes sense, right? So if there is more CO2 in the atmosphere, there's going to be more CO2 dissolving in the ocean. Seems fair. So as CO2 levels rise in the atmosphere, they're going up, dissolved CO2 is going to increase in the seawater. So this part, this green thing, is saying that this is a pH. And so where these two are going up, this is now going down. And so again, I don't really like it when they start midway. You're not starting at 0. So this axis is now referring to pH. It seems to be going down over time. And again, I have suspicions about what's causing this pattern here. So as CO2 levels rise in the atmosphere, dissolved CO2 is going to increase in that seawater, and because that CO2 gets converted to carbonic acid, it's going to make the water more acidic and decrease over time. So this is real data that's being collected out there, and so this is what they're observing, right? So it's going to reduce the pH, which will then dissolve the calcium bicarbonate of the shells of those mollusks, of that coral, and I'm gonna leave these videos for you guys to watch later. So these are some pretty cool ones, especially like this one here. Okay, so that's ocean acidification, but we noticed that there was sort of that jumping, right? Go back. That's happening here, and like I said, I have suspicions about what's causing that, and that's because carbon dioxide levels cycle by seasons. So again, let's look at our graph here. So okay, we're going to read the title carefully, right? Okay, so we have modeled photosynthesis cycle, in the northern hemisphere. Okay, that's the title. And then down here, what do we have? Looks like we got January, February, March, April, May. So it goes to January, so we have 1 full year here and an almost full year here. So x-axis is going to be months. Looks like we've got a couple different locations: Alberta, Canada, Barrow, Alaska, La Jolla, California, and Mexico. Okay, so and then this is, I guess, the modeled cycle. So this is going to be these 4 real data points combined into one. And then over here, again, we have that parts per million CO2 fluctuation. Okay, so, and I'm not really understanding why the 0 is here. That's interesting. Parts per million. How could it be negative parts per million? Okay, well, we'll ignore that for now. Okay, so we start in January, February, March to April, kind of high on this graph. So these are the winter months. And so just think to yourself, okay, CO2 levels are high in the winter. What do you think is going to happen when we enter, say, these summer months? So just take a guess to yourself silently. All right. So what we actually see is this really huge drop in CO2 levels from May to August. And then over the winter months, you have like sort of this creeping of CO2 levels in all 3 of these locations again, although Baja, Mexico, interestingly, does not have as sharp of a drop, although the levels of increase are somewhat similar. But you see it, you know, very strikingly in places like Alberta and Alaska. And then again, we reach a peak in about May, and then boom, it's going to drop again before, you know, during the summer months, and then something happens in the fall and they start creeping up again. So it turns out that what's happening is that photosynthesis is going to peak in your summer months, right? So in May, the April showers bring the May flowers, and all the plants start doing, you know, photosynthesis. And what does photosynthesis remove from the atmosphere? It's CO2, right? So they take in that CO2 while they're growing, and then fall comes and the plants start to die off, and without the plants we start to see this sort of uptick again. They rise really high again in May when springtime hits, and then boom, it drops again. So what I find interesting is that in Mexico the drop is not nearly as steep, probably because those plants survive, right? I mean, if I went to friggin' Alaska in the middle of winter, I wouldn't expect to see a lot of plants. So this fits with sort of what we know. So this is a really cool video, and I'm going to force you to watch it because it is super cool. See if I can get it to come up.
What you're looking at is a supercomputer model of carbon dioxide levels in the Earth's atmosphere. The visualization compresses 1 year of data into a few minutes. Carbon dioxide is the most important greenhouse gas affected by human activity. About half of the carbon dioxide emitted from fossil fuel combustion remains in the atmosphere, while the other half is absorbed by natural land and ocean reservoirs. In the northern hemisphere, we see the highest concentrations are focused around major emission sources over North America, Europe, and Asia. Notice how the gas doesn't stay in one place. The dispersion of carbon dioxide is controlled by the large-scale weather patterns within the global circulation. During spring and summer in the northern hemisphere, plants absorb a substantial amount of carbon dioxide through photosynthesis, thus removing some of the gas from the atmosphere. We see this change in the model as the red and purple colors start to fade. Meanwhile, in the southern hemisphere, we see the release of another pollutant, carbon monoxide. This is a gas that's both harmful to the environment and to humans. During the summer months, plumes of carbon monoxide stream from fires in Africa, South America, and Australia, contributing to high concentrations in the atmosphere. Notice how these emissions are also transported by winds to other parts of the world. As summer transitions to fall and plant photosynthesis decreases, carbon dioxide begins to accumulate in the atmosphere. Although this change is expected, we're seeing higher concentrations of carbon dioxide accumulate in the atmosphere each year. This is contributing to the long-term trend of rising global temperatures. The Orbiting Carbon Observatory 2, or OCO2, will be the first NASA satellite mission to provide a global view of carbon dioxide. OCO2 observations and atmospheric models like GEOS 5 will work closely together to better understand both human emissions and natural fluxes of carbon dioxide. This will help guide climate models toward more reliable predictions of future conditions across the globe.
Okay, so that's pretty cool. All right, so yeah, this data is available. You can check out like any time because they're always tracking it at Maunalao, which I assume is in Hawaii. Those guys have a great job. All right, so last thing is going to be carbon flux. So by far, the biggest carbon reservoir, the biggest carbon sink, is the deep ocean. And so when we talk about carbon reservoirs and flux, when we're looking at the movement, we always measure it in gigatons. So the ocean holds about 38,000 gigatons, and on your sheet, they're actually like in relative sizes. I just didn't like the look of it, so I used a different image for the PowerPoint. But again, 38,000 gigatons is being held by the ocean. All right, so it's the largest carbon sink in existence, right? So the atmosphere, by comparison, has this sort of paltry 750 gigatons. So land biota, so things like the plants and the animals on the land, we hold about 610 gigatons. So remember, we are carbon sinks, we're carbon reservoirs because of those nucleic acids, because of those proteins, and our sugars and carbohydrates, our lipids. All of those are carbon molecules. So we hold about 610 gigatons of the total carbon. And there's all these processes that are going to move them. So like the soil even. So that has like a lot of decomposed matter, has about 1,500 gigatons, which is like considerably more than the living parts, right? And so these numbers here that are tracking the movement, so this means that land biota gives off about 60 gigatons of carbon dioxide per year, and same with the soil. So that's releasing CO2, probably from decomposition of those saprotrophic bacteria. And again, there's only one process that is removing CO2 from the atmosphere, and you can probably guess that that's photosynthesis. That's taking the CO2 out of the atmosphere. And again, these processes are happening in the ocean the same way. Organisms are doing cellular respiration in the ocean, which is contributing to that CO2. That CO2 is going to dissolve out of the ocean and back into the atmosphere. And those phytoplankton that are in the ocean, those are the producers and autotrophs in the water environments, are going to again be doing photosynthesis, and that's the only process that removes it from the atmosphere. Okay. And then finally, and this is sort of a more modern day problem, so the fossil fuels in the shale. So this is the stuff that's just sitting around in the ground, like the oil, the coal, and there's about 12,000 gigatons of fossil fuels that's buried somewhere in the earth. But while it's pretty big, it's still like only a third of the deep ocean, because the deep ocean again is the largest sink, and combustion from that is only about 10 gigatons, but that's enough to cause a problem. All right. So again, here's the overview of the entire carbon cycle. We have both terrestrial carbon cycling over here and the ocean cycling. So for the terrestrial, we have lots of ways to get carbon into the atmosphere, everything from combustion of natural materials like trees, like all the trees that are burning in Australia, to fossil fuels, all of that is going to return CO2 to the atmosphere. Same thing with like the decay of organisms, all the respiration that's occurring from the animals. And then in the ocean, that carbon dioxide is going to dissolve into the water, get picked up by those phytoplankton, which are our producers. We have the bicarbonate that is going to form the calcium bicarbonate, get taken up by those shelled organisms, and then become part of the sediment, become part of that limestone. So that is the entire carbon cycle. Let me know if you have any questions.